Okay, finishing up 18, we were just finished up the continuous compounding and just within compounding periods. So now we're going to move into other applications of exponential functions. Okay, weapon grade plutonium is composed of approximately 93% plutonium-239, called Pu-239. The half-life of Pu-239 is 24,000 years. In a sample originally containing 0.5 kilograms, the amount left after T years is given by this equation. Don't freak out because you don't understand any of that, okay? This is what we need to know, just like everything else. The A sub T is the amount that's left, and the T is our time in years. Okay, it's the amount left after T years. Okay, evaluate the function for T equals 72,000. Well, all you do is substitute that in right here. So we have A sub T, or you can put Y, I don't really care, equals 0.5 times 1/2 raised to the 72,000 divided by 24,000. Obviously, we're going to be using our calculator here. So we've got 0.5 times, good, you can see it on my screen tonight, times 1/2 raised to the 72,000. Make sure I'm typing it in right. 20 divided by 24,000. Make sure I got all the right zeros. It looks right. And we get this amount. Okay? So the amount that's left is 0.0625. Okay, that's one application. Another one, we got modeling growth and decay. Basically, when you look at all these, okay, and it usually will tell you that it grows or it decays at a certain thing, okay, at a certain rate. And we're going to use these formulas right here. The growth factor is related to the rate of change. We've got this formula can be used when the rate of change represents growth, and we have this formula that represents a decay. The only difference in the formula is one's a plus, one's a minus. Okay, so Susie has a petri dish with 350 bacteria. They're growing. Okay, so that tells us we're going to use this one because it's growing at a rate of 17% per day. What is the bacteria population after 3 days? Define your variables, write the functions, represent this situation. Okay, so let's use this function right here. The A times 1 plus R raised to the X. Okay, A represents our initial amount. Okay, so that's going to be 350. Our rate is going to be our percent as a decimal. Remember, you move it left 2 places. So we're going to, this is my R, this is my A. So we have 1 plus 0.17. And it says after 3 days, that's what our X is. We want to know how many bacteria, what is the bacteria population? All right, so again, we're going to use our calculator. 350 times 1 plus 0.17 raised to the 3rd power. Make sure I typed it in correctly. And we're going to have about 561. It doesn't say what to round it to. I'm just telling you, let's do it to the nearest bacteria. Pay attention to your instructions. Right now, I'm your instructions. Okay. All right. Now, Peter has a petri dish with 550 bacteria. They are dying at a rate of 9%. Okay, so this is a decay because they're going down. So we're going to use this formula right here. So again, f of x equals, let's write the formula that we're going to use. Instead of a plus, we're going to use a minus as I write a plus. Minus the rate raised to the x power. Again, a is our initial amount, so it's 550. That's what we start with. Our rate is our percent as a decimal. You move it left 2 places. So we're going to use 0.09 in for R. And what's the bacteria after 5 days? So our 5 is going to be in our exponent. So now we're just going to use our calculators. We have 550 parentheses 1 minus 0.09 raised to the 5th power. Whoops. Helps if I use my caret key. And again, let's just do it to the nearest whole number because I'm telling you that. And so we have 343 bacteria. And that's it. I think that finishes up all of 18.